Okay, so we are on chapter 2, chemistry. All right, so matter and energy. Matter is anything that occupies space and has mass. There are generally 3 states of matter: gas, liquid, or solid. Water is an example of something that can be found in all 3 states as a gas, a liquid, or a solid. And energy is the ability to do work. You have potential energy and kinetic energy. Potential energy is your stored energy. And in chemistry, we store energy in bonds, between different elements. Kinetic energy is energy in motion or movement. All right, so atomic structure. Elements, are composed, or atoms are composed of subatomic particles. Right? So atoms or elements contain protons, neutrons, and electrons. Protons carry a positive charge, neutrons carry no electrical charge, and electrons carry a negative charge. The nucleus is an essential part of the atom. This is where we find protons and neutrons. Electrons move and exist in energy levels radiating away from the nucleus. And the atomic number is always the number of protons in the nucleus. The atomic number is generally, when you're looking at a table of elements, is if you're looking at, let's say, hydrogen, it's either going to be to the upper left or the upper right. I like the upper left, those are the older ones, and I'll have a number 1, 2, 3, 4, 5. That's its atomic number. And that tells you how many protons it has, and when it occurs in nature before it interacts with anyone, it also tells you the number of electrons it has. It may tell you the number of neutrons it has. That number can vary between the same elements of oxygen to other oxygens to other oxygens. So the number of neutrons can vary, but when they first occur in nature, the number of protons equal the number of electrons. Things with mass, we're going to look at that in just a minute, like protons and neutrons, are found in the nucleus. All right, so where you have a little red or a pinkish red little ball there with a plus on it, those represent protons. The zeros, the gray balls with a 0 in it, represent a neutron because it doesn't have a charge. But they're found in the nucleus. In energy levels, radiating away from the nucleus are going to be where we find our electrons with a negative charge. The first electron level or valence shell can hold up to 2 electrons. The next valence shell or energy level can hold up to 8. The third also holds up to 8. And then you bump up to 18 and so forth. But this is not a chemistry class. We're just trying to show you essentially where the electrons would be located. And to a certain extent, it lets you predict a little bit, how different elements will react to other elements in its environment. Excuse me. Okay, so I love these little charts. When I make these and create these, it's for a reason. So, I would practice writing them out, or at least use this to study, to compare and contrast mass and charge between protons, neutrons, and electrons. All right, so anything with mass is in the nucleus. Well, we know that protons and neutrons are in the nucleus, so they have mass. Electrons, very minimal, very minimal. That's why they're found at different energy levels. Charges, protons are positive, P with P, neutrons are neutral or 0, N to N, and electrons are negative. Electrons are negative. Okay, so here we have a hydrogen, helium, and a lithium with the atomic numbers of 1, 2, and 3, respectively. So hydrogen, which we're going to look at, rather frequently, its atomic number is 1, so it has 1 proton and 1 electron. That's the gray ball. Helium has 2 protons, 2 neutrons, and 2 electrons. That first valence shell can hold up to 2 electrons, and that's exactly where we're going to find them. 2 red balls in the center, which are our protons, and then the yellows, are the neutrons. Now, I want to go back to hydrogen, and then we'll take a look at lithium. If a valence shell can hold 2 electrons, like this first one does, it means that hydrogen is going to be very reactive because it is striving to either share another electron with somebody else in the environment. So it fills its outer valence shell, or it will kind of give away that electron. And even though once that happens, I will have one proton and no electrons, so I'm going to have a +1 charge associated with it. It's kind of the path of easier resistance. Initially, the overall charge of this hydrogen is 0 because you have one positive thing and one negative electron. But if the hydrogen is willing to give that electron away, maybe to a chlorine, then it's going to, then it's going to have one proton more than an electron, and it's going to have a positive charge, making it a cation. All right, so that first valence shell can hold up to 2 electrons. Helium isn't going to borrow or give away or anything because that outer valence shell, or that first one, their only one, is full of electrons, and so it's become essentially inert. It's what's called a noble gas. But now we have lithium, and lithium has an atomic number of 3, which means it has 3 protons, so 3 red balls, and it has 4 neutrons right in the nucleus, and it has 3 electrons. All right, so before lithium reacts with anybody around them to share or do whatever, you have 3 protons, so +3, and 3 electrons, -3, and so they cancel each other out. The overall charge to lithium, is nothing. It's neutral, right? Because the 3 electrons cancel out the 3 protons. The first 2 electrons are found in the first valence shell, and the next electron is found in the second valence shell. So this becomes a very reactive entity. Kind of like the hydrogen here, it only has 1 electron and in its outer valence shell. Now, for lithium, this second valence shell can hold up to 8 electrons. So for sure, lithium is much happier with just giving that 1 electron away than trying to share or steal 7 more to fill its outer valence shell. Right, the first valence shell is full, but that valence shell can only hold 2 electrons. So the third one goes into the next orbital level, the valence shell, and that is designed to hold 8. So lithium is going to very readily give that electron away, in which case now we only have 2 electrons, but 3 protons, and the overall charge will be a +1. Again, another cation. That's an element that lost an electron and now has a positive charge associated with it. These are kind of handy to look to see where the electrons would be located and why lithium in this case is much happier with just giving an electron away than trying to share 7 more. I mean, it's just not going to happen. So lithium is a very common cation that we find in chemistry. Excuse me. So electrons and bonds. Atoms are stable if their outer valence shell is full. The first valence shell can hold 2 electrons, and the next 2 levels can each hold 8. Noble gases have a full valence shell and are non-reactive. So once that valence shell is complete, that element is not going to react with anyone. Now, if they have a positive charge, we'll come back to that sort of, because when we talk about ions, they're not going to gain or lose electrons, but they will be attracted and form ionic bonds, an attraction between 2 elements with something that's maybe has a negative charge, like an anion. So those, once you've gained or lost electrons, like an ion will do, it's not going to gain or lose anymore. It's done. However, if it has a positive charge, it will be attracted to something that maybe gained an electron and now has a negative charge, and opposites attract. And that's what an ionic bond is. Okay, so they're all striving to have an outer shell complete. Sometimes it's easier to share because you have 6 out of 8, so you're going to share. If you only have 7 out of, or you have 7 out of 8 electrons in your outer valence shell, and you just need 1 more, they are very likely to steal an electron from someone like hydrogen or lithium that has 1 electron in that outer valence shell. So once you have exchanged, shared, then you generally do not react at all anymore. And so that's what we call being non-reactive. The noble gases, when you look at a table of elements, is the vertical column to the far right-hand side, and all those are noble gases, helium, neon, and they are non-reactive. So electrons will be given away, or taken away, or shared, between atoms to fill their outer valence shell. This is the basis for forming chemical bonds, and they will all do it. They will not just exist like that with just one electron in its outer valence shell. It's going to find someone to give it away and to react with. Okay, so here we have chemical inert elements. These are those noble gases. So an example was helium. So it had atomic number of 2 electrons in the first valence shell. Full, done. Helium is not reacting and forming any other bonds with anybody. Then we have neon, right, which is atomic number of 10. So it has 10 electrons. The first 2 go in the first valence shell. The other 8 go in the second valence shell. And now, boom, that second valence shell is full. And now that element is essentially inert. It's unreactive. But everybody else in here, over to the right-hand side, we have, excuse me, hydrogen, carbon, oxygen, sodium. These are common ones we see. Chlorine. They're all going to be reactive. Right? Because you need to either fill or have empty your first valence shell here with hydrogen. Sometimes they'll share electrons, like with water, or in water, I should say, with oxygen, not with water, with oxygen. Oxygen needs 2 more. Here's in red. Oxygen has 6 electrons in its outer valence shell. It will hold up to 8, so it wants to share 2 more. Right? And if 2 hydrogens are hanging around, then that 1 electron from hydrogen can be shared between the hydrogen and the oxygen, and the same with another hydrogen to the other end of this oxygen molecule. And they will share those electrons between them. And that's what H2O is, a water molecule is. Okay, so the bonding of atoms, the first ones we're going to look at are ions, which I just mentioned. Ions are atoms that gain or lose electrons to become more stable, to fill its outer valence shell. And they become an electrically charged atom, which means that if you are giving 1 electron away, like here we have sodium, it has 1 electron in that 3rd energy level, which can hold 8 electrons. So the path of least resistance is to just let that electron go. And now it becomes unreactive. However, we do have 1 more proton than we do electrons, so it has a positive 1 charge associated with it. That's what we call a cation. All right, so cations are formed when you lose an electron, or 1 or even 2 electrons. If you're the recipient and you gain the electron, in this case, chlorine, it has 7 out of 8 electrons in its outer valence shell. It just needs 1 more, which means it has what's called a high electronegativity. That nucleus, all those protons and those electrons, it is so close to filling its valence shell, it is like a very strong magnet to yank away, an electron from one of these elements, like hydrogen or sodium, that has 1 electron in its outer valence shell, even lithium. Right? They are glad to give it away, and chlorine wants to yank it away. Right? So when you gain an electron, you have now more electrons than you have protons, and thus you have a negative charge associated with it. So anions are formed when they gain electrons. Right? Sodium chloride is an example of a salt. Right? Sodium chloride is not called salt. It is sodium chloride. Right? It is an example of a salt. Okay, so sodium, again here, the same diagram, is willing to give 1 electron away, and chlorine is willing to accept it. And so the sodium has a positive charge and the chlorine has a negative charge. I'm not sure why that PowerPoint is not. I'll have to go back here and just shove this over a little bit. I'm not sure why sometimes when I put this in slideshow mode that it shifts some of the print in here, but I'll take a look at that. And if I need to resave this document for your notes, then I'll go ahead and do that on the course page. Sometimes this, I think, is just my computer, because maybe this is set at 110, % of the image instead of just 100. I'll have to go back and check. So part of my divergence there. Okay, so we're going to look at 4 types of bonds: ionic bonds, polar covalent, non-polar covalent, and then hydrogen bonds. right? So bonds are forces that hold atoms together to form different molecules of compounds. Again, depending on how many electrons are in their outer valence shell, kind of gives you a prediction of which ones are more likely to share or steal or, give away, electrons. All right, so we have the first three, for most purposes, will be the type of bond, an ionic, polar covalent, or non-polar covalent, within one molecule of something. Right? Hydrogen bonds may be within one very, might be found within a very large organic molecule, but it's also the attractive force between other polar covalently bonded molecules. Like, how does one polar covalently bonded molecule interact with another one when it comes upon them? So we're going to talk about that. So hydrogen bonds may be what's either intermolecular or intramolecular, and I'll give you examples of each. Okay, so ionic bonds are bonds between ions, between a cation and an anion. Right? We said sodium was an example of a cation if chlorine is in its environment, because sodium is going to give away an electron and it's going to have a positive charge associated with it. So we have a little positive, the red little positive sign on the left-hand side with sodium. And chlorine accepts or steals that electron and has a negative charge associated with it. So they are not going to exchange any more electrons. However, opposites attract, right? So the positive sodium becomes attracted to the negative chlorine, as long as that's all that's in the environment. So if we have 100 molecules of sodium and 100 molecules of chlorine, they will stagger and interact with each other, similar to this crystalline form we see over to the right-hand side, where you have alternating positive, negative, positive, negative, positive, negatives, sodium chloride, sodiums, and chlorides. So you have to have ions first, an anion and a cation form. And if that's all that's in their environment, then they become attracted to one another. Right? So formed electrons are transferred from one atom to another, and then opposites attract. Okay, covalent bonds. Covalent means to share. All right, but you can have equal sharing and unequal sharing of electrons within a molecule of something. All right, so these are formed when atoms share. If we had two hydrogens and they're the same size, they have the same, atomic number. They have only one proton each in the nucleus. They have one electron in its outer valence shell. Heck, they can agree to share their respective electrons between each other, like over here on the right-hand side. And that essentially kind of pseudo fills this outer valence shell for them both. And those electrons just kind of hover around a little bit back and forth, and they're happy with staying bonded to each other like this. So that's an example of equal sharing of electrons, because they are of the same size. Their nucleus is of the same size. They have the same what's called electronegativity. And so they equally share. That would be an example of a nonpolar covalent bond. But polar covalent bonds occur when you have unequal sharing of electrons. And that happens when you have molecules sharing electrons, but you have some that are rather small and then some that are rather large, that have a higher atomic number. So the example down here on the bottom is water. The two white balls are the hydrogens and the red is the oxygen. Hydrogens have an atomic number of 1. They have 1 proton, 1 electron. So they're small, right? But they're willing to share their electrons, or oxygen is willing to share the electrons, 1 each from each hydrogen, and just be happy with sharing. However, the oxygen end of the molecule is, has a higher, or oxygen in general has a higher electronegativity. So even though it shares, those electrons, each from each hydrogen, will reside at the oxygen end of the molecule more than over at the hydrogens. So the hydrogens end up having a relative positive charge associated with them, both of them. And the other end of the water molecule has a slightly negative end. So that's what I said, slightly negative, slightly positive. That creates, that unequal sharing of electrons creates polarity of charge, opposite charges around this one molecule of water. And that's what we mean by polar covalent bonds. Results when electrons are not shared equally in covalent bonds. Water is an important polar molecule, as well as amino acids, sugars, phosphate groups. We're going to look at that. Right? the molecule with a slightly negative end and a slightly positive end. So the unequal sharing of electrons, because one of them is a stronger magnet or has a higher electronegativity, will have that will be the negative end of the molecule. And then the other two, in this case, would be positive ends. But this kind of unequal sharing is repeated in a lot of the organic molecules we find in our body. And it makes sense because if water is polar covalently bonded, then we would expect most molecules, not all of them, but most molecules in the body to either be polar covalently bonded or have some kind of charge associated with them. So to keep that in mind going forward. Okay, non-polar covalent bonds are created when you have equal sharing of electrons. And this happens in the case of we just saw, let me just go back up here, where the two hydrogens are happy to share. And down here, when we get into the fat family. So lipids like triglycerides, steroids, and cholesterols, they equally share their electrons. So you do not have polarity of charge around those molecules. They equally share. Right? So when you're non-polar, you kind of your neutrals are around the entire molecule. You don't have positive and negative ends. Hydrogen bonds are weak attractive forces between, it may be what's called intramolecular or intermolecular. If it's intermolecular, it's the attractive force between two or more polar covalently bonded molecules. So let me give you an example of, water and then other water molecules. Within one water molecule, you have polar covalent bonds that create the positive and negative ends to that one water molecule. But what happens when it comes across another water molecule with positive and negative ends? How will they interact between each other? Well, the negative end of one water molecule, the oxygen end, will be attracted to one of the hydrogens that has a positive charge. And that's what we mean by intermolecular hydrogen bonds. They're rather weak, but they will line up, kind of like the sodium and potassium, sodium and chloride did, where they're just going to alternate positive, negative, because opposites attract. Well, the negative end of one becomes attracted to the positive end of another polar covalently bonded molecule. Right? Generally, it's hydrogen, that's going to be attracted to nitrogen, oxygen, or fluorine. I just call it NOF. These hydrogen bond attractions can occur between molecules, which is what's called intermolecular, or within parts of a single molecule, a very large one, called intramolecular. So we find intramolecular hydrogen bonds, in large proteins, and in the center of DNA. Right? So this is hydrogen bonds can be formed between water molecules, especially because you're never going to have just one water molecule. You're going to have a bunch, through the center of DNA and within the secondary, tertiary, and quaternary structure in proteins. We'll revisit that when we get there because we haven't looked at proteins, or any of organic families yet. But that's where hydrogen bonds can be located. All right. This is an example of multiple water molecules. Each water molecule is polar covalently bonded. You have created positive and negative ends to these molecules. But how will they react from one to the other to the other? Positive end to a negative end, positive end to a negative end. So the slightly positive ends of water molecules become aligned with the slightly negative ends of other water molecules. And that's how they will orient themselves. You don't have to push them. They're just going to, just orient themselves. Here are a couple of videos, that show you different atomic structures. If you download these notes and you put it in PowerPoint form or slideshow form, I should say, when you click on these, it should connect you. I won't do them right now because we're doing a video here like this, but you can access them that way. Right? And then here's another. I actually just left the addresses so you can copy paste. If you're a dog lover like I am, then you're going to love this. Okay, so let me put this back into slideshow mode where we left off. And we will talk about solubility. Okay, so solubility is the ability of a molecule called a solute to dissolve in another solvent, considered the solvent. And in the human body, our primary solvent is going to be water. It depends on two major variables, the ability of, or the degree of solubility of one substance, like a solute, in a solvent. And it's based on bond type compatibility and molecular size. So, in chemistry, we say like dissolves in like. And this comes down to a lot of these whether something is either ionic, where it has a positive and negative charge, like anion or cation, or something's polar covalently bonded, which means these molecules are going to have positive and negative ends to them. And when they're like that, they like to be around other things with charges on them. So water likes to be with sodium chloride, because we know salt dissolves in water, and you'll see that in just a moment. And fats like to be dissolved in other fats because they're all non-polar covalently bonded. So, bond type incompatibility, if you're non-polar, you have charge, you like to be with other non-polar covalently bonded. Or I'm sorry, if you are polar covalently bonded, or you're an ion, you want to be with other things with charge. And if you're neutral or non-polar covalently bonded, then you like to be with other similarly bonded substances. All right, so that's what we mean by bond type compatibility. And then molecular size. Let's face it, if it's small, it's easy to hold up. If it's a large macromolecule, it becomes really weighty and heavy to hold up. So the solubility of small molecules is much higher than large molecules. Okay. Chemical reactions. Chemical reactions occur when chemical bonds form or break between atoms or ions in different molecules. Catabolism is a term that refers to breaking down large molecules into smaller ones. And anabolism is a term that refers to creating larger molecules from smaller ones by linking these smaller ones together. So we'll look at an example of catabolism, which will be hydrolysis, and anabolism will be dehydration synthesis. Reactants are the starting materials of a reaction, the atoms, ions, or molecules. And then the products are the substances formed at the end of the chemical reaction. Now, it does not necessarily mean that I start with something big and I end with something small, or if I have small things and I see an equation, then it must be I'm putting small things together and making a larger molecule. You have to look at the arrow, right? So arrows in chemical reactions always point to the product. Right. So in the case below here, we have a reactant, sodium chloride, with an arrow, produces a sodium cation with a plus charge plus a chlorine with a negative charge. Those are the products. How do we know that? Because the arrow points to them. If the arrow was going in the other direction, then the sodium and chloride here, that anion and cation on the right-hand side, would be at the tail of the arrow, and the arrow will point to NaCl. That would mean that we're taking the sodium and chloride, we're putting it together to form the sodium chloride. So the arrow points to the product. Okay, so we have two types of chemical reactions. We have dehydration synthesis and hydrolysis. All right, dehydrate means to remove water, and synthesis means to put it together. So when we have dehydration synthesis, we're essentially taking two molecules and we're going to bind them together to make a larger one. All right, so we're going to do that by the removal of the equivalent of one water molecule. We're going to bind them together. We're going to form a bond between them, and we're going to store energy in that bond. Because bonds store energy. It's a type of potential energy. Hydrolysis is the opposite. Hydro means water, and lysis means to break apart. So this is what we're going to do. It's exactly the opposite of what we did in dehydration synthesis. We're going to start with a larger molecule, and we're going to chop it into pieces, maybe just two pieces, maybe multiple pieces. All right, so we start with something large. We end up with smaller molecules, maybe 2, 3, 4. It just depends. We do so by adding water, or the equivalent of one water molecule. We break apart the molecule and we release energy from the bonds, that we had formerly created. So we release energy. All right. This, I like this because it has two amino acids to the left-hand side. So we have amino acid plus an amino acid. All right, we have two arrows. The top arrow goes from left to right and points to the dipeptide. So what happens is if we want to link together those two amino acids, follow the top arrow, that reaction says in there in blue, dehydration synthesis. We are peeling off, we're removing the equivalent of one water molecule, so H2O peels off. And now we have created a bond between those amino acids, and that becomes a di for two, dipeptide. It's called a peptide bond. It's a type of polar covalent bond. That's as far as you have to know about peptide bonds. It's each amino acid, like within one water molecule, right? Within one amino acid, we are polar covalently bonded. And so therefore the product will also be polar covalently bonded. And you can see how we're removing from one amino acid an OH group and a hydrogen from the other amino acid. That is the equivalent of H2O, water. We open up an area to create a bond, and that's where you're going to store energy in the bond that's created. Now, we can also go the opposite way from a dipeptide, from the right back to the left. That's the lower arrow, going right to left. That is hydrolysis. So now what we're going to do is we want to do the opposite. We want to take this dipeptide and chop it in half. All right? So we're going to add the equivalent of one water molecule. That breaks the bond. And now we have released some energy. And now we have two separate amino acids. So you can go back and forth. The arrow points to the product. Okay, factors affecting chemical reactions. Well, we have enzymes. Enzymes are a type of protein that increase the reaction rate of creating a new substance by lowering what's called the activation energy. And essentially what it does is that enzymes will have specific binding sites for the two molecules it wants to join together, right? And if you can do that, where you have enough substance, so the next factor is concentration. The more the substances you have in an environment, the faster you can bond them together and produce a new product. Meaning, if I have 5 molecules of sodium and 5 molecules of chlorine, in a beaker or something, and I want to bind them together, is that it's going to be harder to get these little sodium chlorides to collide with one another and allow them to exchange electrons and then, have that attractive positive to negative ionic bond created. If I could have them bind to an enzyme, which then brings them together very, very quickly, then I can produce my product much more rapidly. The more concentration I have, the more sodiums and chlorides that are available in the environment, that speeds it up as well. So if you have instead in the same volume, instead of having only 5 sodiums and 5 chlorines, that with the potential of only making 5 sodium chlorides together, if I had 100 sodiums and 100 chlorines, now I can make, form 100 molecules, and that will increase my rate of reaction. I will produce those much faster. So the more substrate you have, so to speak, the faster, the faster your reaction rate. So enzymes bring stuff together. I'll show you what it looks like when we get to the proteins. That increases your chemical reactions. The concentration, the more you have of each substance, the faster you can produce a product. The size, the smaller they are, the easier they are to move around, so you can produce a product more quickly. Temperature to a point. Increasing the temperature will speed up molecular movement and cause the reaction rate to increase to a certain point. You don't want it to be too hot. You want it to be the right temperature. And every chemical reaction has kind of an optimal pH and temperature in which these chemical reactions will occur. So, but you generally don't want them too hot, because we will essentially break apart our enzymes. And we'll talk about that when we get to proteins. And the other factor is pH. The low, extremes in pH, especially low pHs, will also break apart our enzymes and ultimately slow down the reaction rates. So there's an optimal temperature. Generally, warmer is better, but not too hot. You don't want it frozen. If you're in frozen water, nothing's going to happen, right? But if it's warmer, then you start to increase the chemical reaction. And the same with the pH. You want it to be an optimal pH. What we're going to consider optimal is about the pH of your blood, 7.35 to 7.45. Okay, that takes us to a Kahoot quiz. We do these in class. Obviously, I'm recording this with you, and there are no players. But if you sometimes look, if you look through some of the notes and they still have this Kahoot in them, then you can put it in slideshow mode like this, and then you click on it, and it will allow you to go into this quiz. Okay, then we're going to talk about the chemical constituents of cells, organic versus inorganic. Okay, so we were talking about solubility. We're talking about reaction rates. I talked about that little Kahooty Doody quiz. Now we're going to talk about organic versus inorganic molecules, and then we're pretty much done. Okay, so inorganic molecules usually dissociate in water, forming ions, but they may not. Right? So they may be something like other water molecules. They're inorganic. Oxygen, different gases like oxygen, carbon dioxide, and others called inorganic salts. Organic molecules contain at least a carbon and a hydrogen. So you have to have carbon and hydrogen to be organic. And that includes, especially in the body, carbohydrates, proteins, lipids, and nucleic acids. Those are our four, major organic categories in the body. So inorganic things are like water, which is the most abundant compound in living material. It's the primary solvent of the body. Right? It's a medium for most metabolic reactions, chemical reactions. And it absorbs and transports heat really well. So water is a very important substance. Oxygen is required to release energy from nutrients and metabolic activities. When we look at cells, the mitochondria, sometimes in high school you call it the powerhouse of the cell. It's in the mitochondria that we're going to take some of these sugars and we're going to combine with oxygen at different stages is change those molecules into energy currency called adenosine triphosphate, or ATP. Carbon dioxide is a waste product released during metabolic reactions and must be removed from the body. And as I just described, I said in the mitochondria, powerhouse of the cell, we're going to take some sugars, and other molecules can be used to be burned. But right now we're talking about sugars with oxygen to produce that ATP. Well, a byproduct of forming all that ATP is carbon dioxide. So this is where all this carbon dioxide comes from that you have to exhale away, and eliminate from the body. And then we have other inorganic salts that are abundant in the body, sources of necessary ions like sodium, chlorine, potassium, calcium, and so forth. All right, electrolytes, acids, and bases. So electrolytes are ions in solution, essentially, anions and cations. If I take some salt, like a sodium chloride, and you can use the example of table salt, and you throw it in water, especially with a little heat under it, those salt crystals are going to dissolve, right? We said the like dissolves in like. Sodium chloride, because can break apart to a sodium plus charge and a chlorine negative charge, it's going to want to be in another substance that has charges associated with it. And water is perfect because it has positive and negative ends to the molecule. Right? So once you put salt in water, it can separate and be soluble. And so the sodium, positive sodium, will be attracted to the negative oxygen end of a water molecule, and the chlorines with a negative charge will be attracted to the hydrogen positive ends of a water molecule. All right, so that's what electrolytes are. You've often heard this, different drinks you can get with electrolytes after you work out and stuff like that. Acids are substances that dissociate to release hydrogen ions when in water. So kind of like what happened there with sodium chloride, if I put hydrochloric acid, that's what HCl is, if I put it in water, it too will split apart in the center. The hydrogen will dissociate from the chlorine, and again, the H positive will be attracted to the oxygen end of a water molecule and the chlorine to the hydrogen ends because opposites attract. The fact that this releases H pluses from that chemical formula there, HCl, we predict that it's going to release those H pluses. A substance that does that is an acid, because that level, the number of H pluses can increase or decrease, and that changes the pH value of a solution. Yes, you're going to have these chlorines there, but we don't care about it because those H, the chlorines with a negative charge does not affect the pH value of a solution. Bases are substances that release hydroxide ions. Those are the OH negatives on the bottom there. All right, so hydroxide ions can combine with hydrogen ions to form some water. Right? So a base, like sodium hydroxide on the left-hand side, the NaOH, is a base. If, again, I put that in water like I did with the other substances above, it will break apart. Right? The sodium will take off by itself, be attracted to the oxygen end of the molecule because it's negative, and the OH negative will be attracted to the H pluses. The fact that this substance, NaOH, will dissociate and release OH negatives make it a base. All right, so I think you know where we're maybe going with this. If I have 10 hydrochloric acids, that means I'm going to have the potential of releasing 10 H pluses, so you have a 10 positive charge. If I have 10 sodium hydroxides, I'm going to be able to release 10 OH negatives. That's 10 negative things. The H pluses can combine with the OH negatives and cancel each other out, as well as the chloride, the chloride ion here negative to the sodium positive. But it's the H plus and the OH negative. The ratio of those two to one another determines the pH value of a solution. The chlorine negative and the sodium positive, that anion and cation, they're going to be reattracted to one another again, and they can be, but they don't affect the pH of the solution. Yes, that contributes to different electrolytes, to different, anions and cations, but it doesn't affect the pH value of a solution. Right? Here we have water molecules over to the right-hand side, and what happens if I put some sodium chloride in there? Now the sodium doesn't have to just be attracted to chlorine. Sodium can be attracted to, again, the negative ends of water molecules, and they disperse from each other, and that's how they become dissolved. Ions in solution. Okay, so here we have our picture of the acid-base concentration. The pH scale indicates the concentration of hydrogen ions in solution. In reality, it's the ratio of the red area here to the blue area. The red area represents the hydrogen ion concentration, the blue, the hydroxide ion. So up in the upper left-hand corner, it says acidic H plus, and down in the lower blue, lower right-hand corner are the OH negatives, and this says that's basic. So the blue represents the OH negatives, the red, the H positives. All right, the pH scale is 0 to 14 on the bottom, and in the middle is neutral, where your red area hydrogen ions equal the blue area OH negatives, it means they cancel each other out. If I have 25 H pluses and 25 OH negatives, they just cancel each other out. They're going to essentially form the equivalent of 25, whatever, 10 water molecules, and you are neutral. You're just zero. Right? That's what the middle of the scale is at 7. Right? But as the hydrogen ion concentration decreases, so look at the red, where the red area starts to become smaller and smaller, the blue area becomes bigger and bigger. So they're proportional to one another. Right? And as the red area gets smaller, the pH value we're assigning to the solution down on the bottom starts to increase from 7 to 8 to 9 to 10 to 11, 12 to 14. Right? From 7 to 14 is considered the basic or alkaline end of the scale. And we assign those numbers because the hydrogen ion concentration is decreasing in red and the blue is increasing. Right? So the red gets smaller, hydrogen ions decrease. Right? The blue area gets bigger. The value assigned to the solution is increasing. But let's say we stop at like number 11, all right, we're at a pH value of 11, and we increase the hydrogen ions in the solution, where the red area is becoming larger and going to the left. So I'm going from maybe a value of 11 to 10 to 9 to 8 to 7 to 6. As the hydrogen ion concentration or quantity increases and the red area gets larger, the blue area gets smaller. And the value we are assigning to the solution is decreasing from maybe 11 to 10, maybe all the way down to 1 or to 0. Okay? Values, whether you're on the acidic end, which is 0 to 7, or the alkaline end, the closer you are to 7, the weaker the acid or alkaline solution you are. So let's say, we're at a pH value of 6.5. Technically, we're on the acid end of the scale, but we're really not far from neutral. I mean, we just have some more hydrogen ions than we do the hydroxide ions, which makes us a weak acid. And the same for a base, like our blood, the average range for blood is 7.35 to 7.45. Yes, we're on the alkaline end of the scale, but it's not a strong base. It's pretty much neutral. It's just a little on the alkaline side. That's what our blood is like. Right. Now, the indicators we use for determining pH is really measuring the hydrogen ion concentration, not the OH negatives. So we have tables for all these different acids and solutions, where we can kind of predict what the pH is. But we are using like a litmus paper that's responding to the number of hydrogen ions present in a solution. And that's why we generally describe the changing levels of hydrogen ions, not the hydroxide ions, because that's what our indicator paper is really measuring. So as the hydrogen ion concentration increases, right, and you get a larger and larger red value, the red area, the pH value of the solution is decreasing. When the hydrogen ion concentration decreases, so the red area starts getting smaller and smaller, the value we assign to that solution is increasing. Right? Acidic, neutral means we have a pH of 7, indicates equal concentration of H pluses to OH negatives. Acidic, means that we're at a pH less than 7, indicates a greater concentration of hydrogen ions. Weak acids are close to 7. Strong acids are very far away at the extreme end, like at 0, 1, and 2, and 3. And the same for the bases. The farther you are to the right, where you get to values of 12, 13, and 14, where you're pretty much all OH negatives, those are very strong bases. Right? And those are very caustic in the body. I mean, look, you have examples of ammonia and stuff. I mean, those are also kind of organically structured, but yeah, they're pretty, they can cause death. And so it's not just acids you have to worry about. You have to worry about extreme bases as well. But there's, different strengths, of these acids and bases. And this is just kind of a table that shows you in a linear, vertical direction, we should say, when we're here at neutral, what are some examples of common things that, you might find in your household, like bleach and ammonia, what their pHs are, and things that are common acids, that you can find in your house. Okay, neutralization of buffers. Buffers act as acids when the pH is high, and bases when a pH is low to stabilize the pH. Okay, so buffers essentially are designed to help maintain a particular pH of a fluid. Some buffers are good at keeping certain fluids, let's say, at a pH like blood of 7.35 or 7.45, or they can act to help maintain a pH of maybe 8.5 or 4.2. It just depends. Right? But they help to stabilize a particular pH. Okay, so we're going to talk about organic substances like carbohydrates, proteins, lipids, and nucleic acids. Okay, so we're going to talk about, again, we're talking about organic families. Let me just scroll down a little bit. Okay, so let's talk about carbohydrates first. For each of these families, we're going to identify the building blocks, intermediate molecule, if they have one, and then the macromolecules. So we're going to start with carbohydrates. And I'm going to start off by saying all these carbohydrates, because they're composed of sugars, they're all polar covalently bonded. So they are water soluble. Right? Polar covalently bonded. They are water soluble. All right, that building blocks of a carbohydrate, the smallest repeating unit, right? It's called a monosaccharide, one sugar. That includes glu-through-gal-ribose, glucose, fructose, galactose, and ribose. And their function is to act as a source of quick energy within those cells. So those mitochondria in cells, they love glucose. That is the preferred molecule. Right? But we can burn other sugars and other amino acids and fats even for energy. All right, so the building block, monosaccharide, glucose, fructose, galactose, even ribose, and its function is quick energy. The intermediate molecules, two sugars together, those are disaccharides, sucrose, lactose, maltose. And the macromolecule or large size molecule is a polysaccharide, many sugars. In the body, we call that glycogen. And in plants, it's either considered cellulose or starch. Its function is short-term energy storage. So this is what happens. We eat, some of these vegetables and things, or potatoes, which is starch. That is a polysaccharide. We break it down, by chewing, and we add enzymes, and we break it down ultimately to monosaccharides, to glucose. Those glucose molecules can now be absorbed in our small intestine, and it can be transported and utilized by other cells in the body. When we have kind of allowed all the cells to take up as much glucose as it kind of needs, right, then the excess glucose will then be taken and linked back together again to form another polysaccharide chain of glycogen. And that's what we store in the liver and in skeletal muscles and save for later for when our glucose levels drop down low and now we're getting hungry again, we need more glucose. Right? All right, so glycogen is the storage form of carbohydrate in the body. We often eat things like starch because that's from plants. But once we've used up as much glucose, as we need from that starch, we will then take those little monomers, those monosaccharides, and dehydration synthesis, put them back into a long chain of polysaccharides and store them for later. So that's why we call it short-term energy storage. Long-term energy storage will be fats. All right, glycogen is the storage form of carbohydrates in humans, and starch is the storage form of carbohydrates in plants. I would be familiar with what mono, di, and poly mean. One, two, or many, and saccharide means sugar. Okay, so this is an example of a polysaccharide. We have a lot of these organized on the cell surfaces. We'll talk about that when we get there. But these are linked chains of these monosaccharides. So you link a long strings of them together, and it's a polysaccharide. Okay, that takes us to the protein family. Proteins, amino acids, and therefore all proteins, are polar covalently bonded. If our building blocks are polar covalently bonded, our intermediate and macromolecules will also be polar covalently bonded. All right, so they're polar covalently bonded, they're water soluble. The building blocks are amino acids. The intermediate molecular form is a dipeptide, and the macromolecules are called a polypeptide. An important example of that in the body is albumin. Now, there are 20 different types of amino acids to build all these proteins. And I will tell you that proteins, that family, has the most diversification to it. I will say there is a limit to the number or the types of proteins that you can make. But when you have 20 different amino acids and you can have different structural organization, we're going to talk about the primary, secondary, tertiary, and quaternary structures, is that there are all these different molecules that can be made, and each molecule has different functional capacities. So that all the molecules in the body that have unique and sophisticated complex functions are going to be proteins. Now, proteins are susceptible to very low pHs. High pHs also, extreme high pHs, but low pH in blood is more common to happen than in areas of the body than high pH. But we could just say safely, extreme pHs, especially low pH, and high temperatures, risk breaking down these proteins. And it's called denaturation. Denaturation is when we break the hydrogen bonds within proteins and they start to unravel. So proteins are susceptible to denaturation, which is due to one or both, either extreme pHs like a low pH and or high temperatures. It breaks these hydrogen bonds that I described before. Okay, so proteins also not only form albumin, which in red here maintains an osmotic gradient, you're going to get that in AMP2 again, but it forms hair, nails, muscle, hormones, receptors, enzymes, antibodies. Hormones, receptors, enzymes, and antibodies are very, very specific, right? They have to be made exactly right or they won't function correctly. So again, very sophisticated function. Amino acids are held together with polar covalent bonds, which is a type of peptide bond. So the amino acids have positive and negative charges associated with them. And as you string them all together, you start to have a whole series, maybe 100, 150 amino acids in sequence that have positive and negative ends to them. That is your primary structure. And I'll show you that in just a second. This is an example of an enzyme. I said that enzymes are proteins and that they will have these binding sites on them generally. It may be two of the same molecules, so you can bind them together. It could be two different molecules, but each binding site has this active site. Each of those holes on that enzyme to the left is for a particular molecule. And as long as they're in high concentration, they're abundant. Once they kind of plop into those openings here in the second diagram where below it says number 1, substrate binds in an active site and temporarily forming an enzyme substrate complex. Blah, blah, blah. So the amino acids fall into those holes, so to speak. And then that enzyme, boom, it creates a bond between those two enzymes and then just spits it out and releases it. Well, it doesn't spit it out, but you get my point. So it facilitates dehydration synthesis. I'm removing water. I create a bond between those two amino acids and boom, you let it go. And that is your product. That enzyme is now ready to go and bind to two more molecules and boom, release another dipeptide here. And that's how enzymes increase chemical reactions. And they're very, very important in the body. We couldn't survive without them. Okay, so we have with proteins, more about proteins, because this is where you have the most diversification. You have 4 levels of organization. You have a primary structure, a secondary, tertiary, and often a quaternary structure. So the primary structure is the sequence of, let's say, I need to string 125 amino acids, on a string. And I have 20 different amino acids to choose from because I said you did. And each one here is represented by a different colored bead or amino acid. So the first 125 on a string, like you're making a very long necklace, is your primary structure. Now remember that each of those beads, those amino acids, have positive and negative ends associated with them. So what do you think is going to happen if you can't keep it taut and in a straight line? If it starts to fold on itself, like it's showing here, like a wave, is that as one amino acid, positive, negative, becomes close to another amino acid with a positive, negative end, the positive of one is going to be attracted to the negative of the other, and they're just going to twist and turn, and they're going to form this hydrogen bond. That is an example of a hydrogen bond. The attractive force between one polar covalently bonded amino acid to another one farther down the chain. And now, boom, they come together and they hold that structure. So the secondary structure is the shape that it forms. It might be in a beta pleat like this, in kind of an accordion, or it could be in a coiled structure like DNA, a helix. All along the way, right, they're going one positive end of one amino acid will become approximated to the negative of another, and boom, they form this hydrogen bond. And that maintains this accordion kind of a pleated structure, or the coil. Now picture that, let's say 2 feet long. Now what I can do is I can kind of form a knot, kind of like a pretzel, and that forms this tertiary structure. So again, now we're going to let it kind of recoil on itself, and for the same reasons that form the hydrogen bonds, in the secondary structure, the exposed positive and negative ends of these other amino acids farther down, down the helix or down the accordion pleat, will be attracted to someone farther down as well, positive and negatives. All right, so it's going to maintain now like a pretzel shape of a long coiled structure. That's its tertiary structure. Then we maybe take multiple tertiary structures, like multiple pretzels, and we bring them together. And for the same reasons, positive ends of one pretzel is attracted to the negative end of the other, another hydrogen bond, and it keeps that shape. Those are required for these proteins to do their job. If the temperature goes too high or you have very extremes in pH, especially low pH, the bonds that keep those together, those positive and negatives between these different amino acids, dissolve, and you go from maybe a quaternary structure to the tertiary to the secondary, and possibly into a primary structure, and now they can no longer function. So proteins are very susceptible to this. Why is that important? It's important. This is one of the vital signs you take in a patient to look at body temperature. If body temperature is elevating too high and is staying there, you need to drop that body temperature because you start to denature your proteins. Okay, one of the third family we're going to look at are the lipid or fat family. Fats are non-polar covalently bonded, so they are insoluble with water. They will be soluble in other fats or other non-polar covalently bonded, or neutral substances. Okay, so lipids and our last category go from macromolecule to building block. There is no in between. So our neutral fat is called a triglyceride. It's also the macromolecule. It's a large form. Now, triglycerides function, like all fats, as long-term energy storage, cushion, and insulate organs. All right, the building blocks of one triglyceride is 1 glycerol and 3 fatty acids. The glycerol is a 3-carbon chain molecule. On the bottom here, we have the glycerol portion. In the darker tannish kind of a region, you have 3 carbons bound together. That is the glycerol portion. And attached to each carbon is this long fatty acid chain of carbon to carbon to carbon to carbon chains with hydrogens attached to them. Those are the fatty acids. So it's like a tripod. Okay? So our neutral fat is called a triglyceride. The building blocks are 1 glycerol and 3 fatty acids. The macromolecule is a triglyceride, and its function is long-term energy storage, cushion and insulate organs. It is non-polar covalently bonded, so it does not mix. That's why fats don't mix with water. Now, we can take one of those triglycerides and modify it. It's called a modified triglyceride, and that produces a phospholipid. Now, phospholipids we'll look at in the cell chapter, are the components of plasma membranes or cell membranes. And it too, again, goes from a building block to a macromolecule. It's very similar to a triglyceride. The building block is a glycerol molecule. Instead of 3 fatty acids, it's just 2. And we're going to substitute a phosphate group, which is called a PO4 group. All right, that phosphate group is polar covalently bonded. The glycerol and 2 fatty acids are non-polar covalently bonded. All right, so the building blocks are 1 glycerol, 2 fatty acids, 1 phosphate group, and the macromolecule is called a phospholipid. So I say here, they are the combo pack of polar and non-polar covalently bonded regions in the molecule. All right, so you have to know which parts are polar covalent and which are non-polar. Well, I told you the phosphate group is the polar covalently bonded end. And to the lower right-hand side, that ball with the 2 little tails, that's the symbol for phospholipids for almost every textbook you see. Right? The ball end represents the phosphate group, which is polar covalently bonded, and therefore it likes water and is hydrophilic. The 2 tails there are the fatty acids that are non-polar covalently bonded, and thus they hate water, they're hydrophobic. The tails will point toward one another in a plasma membrane. And we'll see that again in the next chapter when we look at cells. So the function of these phospholipids is a major component of cell membranes. To the lower left-hand side, we see a triglyceride, the 3-carbon chain, and attached to each one, fatty acid, fatty acid, fatty acid. Right? If I take one of those fatty acids off and I put the phosphate group, that takes us to the image in the center. You see that PO4 group? That represents where the ball is there. That is polar covalently bonded. The rest is non-polar covalent. Your hydrophilic, hydrophobic ends of the molecule, that is a phospholipid. Okay. The last thing I want to cover about fats is that other than triglycerides, we have things like steroids and cholesterols that are kind of in the same family. A steroid kind of looks like 4 stop signs in a row bound to each other. So to the lower left-hand side, you see it kind of looks like 4 stop signs. That would be a steroid. A steroid with these other carbon chains kind of attached to them, those are cholesterols. Now, it's normal to have, we need a certain amount of cholesterol and steroids in the body. We have hormones that are steroidally based. Steroids will be found between the fatty acid tails and the plasma membrane, and it helps give it some support. So it's normal to have those. It's healthy. We need to have those. We just don't always need to have as much fat in our diets, that we do. Okay, the last family are the nucleic acids. And again, we have building block and macromolecule. The function of our nucleic acids, this includes DNA, RNA, is that it carries genetic material and our genes. And these genes, and the DNA code for essentially the recipes to make all these proteins. Because they're quite complex and they're very specific. And so we have, essentially, I think about, DNA as being, a great big cookbook with each page is the recipe for a particular protein that cell is going to need. Right? And that DNA stays in the nucleus, unless the cell is replicating. If we need to make some more proteins, then we're going to form some RNA, which is like a photocopy of the DNA. They can leave the nucleus, and we will talk about that in cells. We'll talk briefly about protein synthesis. Okay, so the function is to carry the genetic material and amino acid sequence of proteins. The bond type is primarily polar covalent bonds because we have a lot of ribose sugar in there. So the primary bond type is polar covalent, but through the center, of DNA, we have hydrogen bonds. The building blocks are called nucleotides, and the macromolecules are either DNA or RNA, but they're both composed of these nucleotides. Right? DNA is the double helix, RNA is the single helix. Okay, so we can see this is an example of DNA, the double helix right through the center is where we have hydrogen bonding. Okay, adenosine triphosphate. This is our energy currency of the cell. It's a large molecule with 3 phosphate groups. The last phosphate in this chain has high energy, or a significant amount of energy stored in the bond between that last phosphate group and the other two. Right? And when you break that, it releases a lot of energy to perform different active processes, to perform work in the cell. So it's like having a wad of single dollars, and you every time you want to do something, it costs $1, $1, $1. Well, that our monetary currency helps pay for things. Well, in a cell, it's going to use adenosine triphosphate. When glucose is broken down in the cell, like I said, with oxygen by that mitochondria, it produces many molecules of ATP to pay for all these different pumps and muscle contractions and for enzymes to work and so forth. There's always activities in the cell that have to be paid for somehow. That's why we take in calories. That's why we eat food. Is because our cells need to have these molecules along with oxygen. So that's another reason why we breathe, is to take oxygen in, but also to get rid of the carbon dioxide that we have now built up because we're making ATP. All right, that takes us to our last Kahoot. You can try to review that on your own. And that is the end of our chemistry.